Good afternoon, studenten. My name is Dr. Thalassemia, and I'm here to present to you Dr. Thalassemia's Fun with Blood. So, of course, we don't really call it fun with blood, especially if we work in a clinic. Really, what we're dealing with here is the study of hematology. That's the correct word for it, the study of blood. It's hematology. And for today's lab, I'm going to demonstrate to you the three main tests that we do for this. There are all sorts of things you can test for in blood, and you know that probably from experience. However, blood is separable into blood cells and blood plasma. Okay, we're just talking about, for today's lab, the blood cells. Testing the blood cells, the hemoglobin, and this allows us to diagnose types of anemias, several of which you're probably already familiar with. Perhaps hemolytic anemia, or perhaps, pernicious anemia, maybe. We'll get to that later. But in terms of the actual testing, the first experiment, or the first test we're going to do, which is also done clinically, is the test for red blood cells, specifically a red blood cell count. And I've got the materials already set up that I need to do a red blood cell count. They consist of, number one, red blood cells. Got a vial of blood here. This is not human blood, not for the classroom. This comes directly from a real live dead sheep. In addition, I have this. This is a diluting chamber. We have to dilute these red blood cells because if you just smear them onto a slide and look at them, it's going to look like nighttime. So we have to dilute them and spread them out to even see them. That's what this is for. And finally, we have this. This is a thick, special slide. It looks like it's made of Coke bottle glass. Fancy term for this is hemocytometer. Sometimes they just call it a blood cell counting chamber, but the fancy word, hemocytometer. Okay, hema for hemoglobin, cyto, cell, a red blood cell counting slide. All right, the preparation for this is actually very, very simple. And it's very simple because this apparatus, these two plastic gizmos are sold clinically. They're for clinical laboratory tests. They're designed to make it easy to do in a lab situation, especially if you're busy. So it doesn't involve all the glassware and pipettes that if you had to do it from scratch. So I'll show you the technique for using this. It's really convenient and easy. First thing, we have this is part of what comes with the kit. Okay, to me, being a guy that kind of looks like a rocket ship. So what I'm going to do is I'm going to take this rocket ship and I'm going to go like this. Push it in, boom, like so. Now it looks like it's impacting and about to explode. Trying to not to give Kim Jong-il too many ideas here. But what that does is it punctures this little container. This is our dilution chamber. So I pull that out, it's now punctured, and then I separate the first stage from the second stage of the rocket, like so. You can jettison this and it can go flying into orbit. This is the part that we need. This contains a little tiny plastic capillary tube. And I'm going to use that capillary tube in order to fill it up with blood. Since I'm right-handed, I have to shift a little bit. The idea being, I can fill any capillary tube using capillary action. So thanks to capillary action, which is really surface tension and the attraction to the walls, I can fill it up like so. I don't want to overdo it. And now I've got this skinny plastic part all filled with genuine sheep's blood. What I do now is I take that and I insert it, twist it up, 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 down. There we go, into the reservoir. And I forgot a critical step. I'm going to pull this out just a little. I'm going to squeeze this a bit because now the blood's in the tube. I want to suck it out of the tube. And it goes out of the tube into this reservoir of fluid. It's pretty basic. It's mostly just water. A little bit of preservative. This gives us the proper dilution, a 201 dilution of blood cells to water. This is more realistic to work with. Okay, so I'm going to mix it up a little bit, like so. I'm going to mix it a little bit more. I'm going to suck more fluid out of the capillary tube, like that. And again, this is designed for convenience. I'm going to pull this around. I'm going to take it out, flip it around like so, and stick the other end on here, and now it becomes a handy-dandy blood dispenser. I love it. So convenient. So now I'm going to use my new blood dispenser, and I'm going to dispense it onto this slide, specifically the hemocytometer. And the way that we do this is different from normal. The way that you were taught in general biology was you take a slide, you put some stuff on it, you make a sandwich, you put the cover slip on top. And there you go, amoeba sandwich. No, not for the way we do it here. This has all been calculated and calibrated for a specific volume of blood to be on the slide. To make that work, we put the cover slip on first, which I've already done. And so then we add a couple drops of our bloody solution. Or if you're in Britain, it's our bloody solution right here, right? And we twist this a little bit. There's little tiny notches to make it easy. I don't know if you can see them, probably not. I'm going to put this bloody drop into a notch here. 1 or 2. I'm going to slide this over because I moved it too much. And sure enough, I'm making a mess, but that's okay. They've already figured that out. That's why it's got 2 sides. If you screw up on one side, you can flip it around, which I did because I'm not used to being on camera. I was never invited to the Tonight Show. And so I'm going to add some fluid to this side of it. I don't know if you can see it, and now it's getting pulled across by capillary action. So capillary action here, capillary action here. If you get it right, and it took me 2 tries, then it sucks the blood and the liquid all the way across the slide. And let me tilt it here and show it to you just a little bit. It sucked it all the way across the metal part. The metal part is what we're concerned about. On the metal part of the slide, there's this little microscopic grid that's been microscopically etched. We want the blood to cover up the grid, so when we count the slides, we see the grid. And we don't end up counting a bunch of air bubbles. So we want the blood to go all the way across the metal plate, all the way across the grid. Otherwise, it's useless to us. And again, that's why we have 2 sides of the slide. I managed to screw up at the beginning. If you put this on your microscope and you find that it's not looking right, all you see is air bubbles, then all you have to do is pull it out, switch it around, put it back in, and look at the other side without having to make a whole new slide. So I won't show you how to count these under the microscope just yet because I don't have a microscope in front of me. That's where Google comes in. I'll show you some nice big JPEG files of sheep blood cells on top of a hemocytometer. So you can do a virtual at-home red blood cell count. Unfortunately, at home, you probably won't have one of these. These are really nice. This is a colony counter. And what you do is if you're counting things like red blood cells or bacterial cells, you just kind of go click, 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 click as you're looking at them. So you don't have to think to yourself, 512, 513, 514, 515. You just focus on what you're focusing on. Looking through the microscope, focused on those tiny blood cells, going click, 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 till you've counted enough on the grid. And then you take that number and you work with that number to calculate the red blood cell count. Pretty basic, sort of, except this is hard on the eyes. You have to take a break every now and then. All right, but the microscopy, I'll show you that virtually, thanks to Google. The next thing that we're testing for over here is, there's 2 words for it. Technical term, hematocrit. Common term, packed cell volume. So what we're trying to determine from this is literally the packed cell volume. Let me get my blood. And of course, you know from anatomy, blood contains red blood cells and plasma. An important clinical measurement is how much of it is really red blood cells versus how much of it is just plasma. That's a big difference. You want a lot of red blood cells, you want a lot of hemoglobin to carry the oxygen. If the hematocrit comes out to be low, the first thought you would think of is, boom, anemia. not enough red blood cells. So I'm going to show you how to prepare the slides first. Excuse me. The capillary tubes, because you have to set them up first, and then they go into the centrifuge. We spin them around and get our packed cell volume. So what I've got here is, lo and behold, capillary tubes. And I'm going to pull one out like this, hold it sort of carefully like this, switch it around so it works out right, like this. And then once again, all I need is like one drop of blood, and it's going to get sucked into the tube by capillary action. See? Told you. There we go. Don't want to go past the red line, just like driving a high-performance car. The idea being, the convention is we want to plug up that area where the little red mark is so that the blood doesn't go flying all over the place when we go to centrifuge it. So I'm taking this. It's a container full of clay, and I'm keeping this capillary tube horizontal so the blood doesn't spill out and make a mess. And I'm sliding it up to the clay, and I'm sticking it in, and lo and behold, I'm going to do it once more. Come on, baby. We get a nice white plug of clay in the end of our capillary tube. It's supposed to keep the blood from flying out. Okay, so I'm going to take that now and I'm going to put it into the centrifuge. It has a metal lid and a plastic lid. This metal lid is for safety. Okay, so I'm going to put it in the centrifuge now, and I want to put it, excuse me, so the white clay end is facing the outside because it's going to be subjected to a lot of centrifugal force. Okay, I'm going to put it in there like so, which you can't see it, but that's okay because I can. And then I'm going to make yet another one. Oh, they're stuck together. Like so. Once again, I'm going to try to fill it with capillary action. Dum-de-dum-dum-dum. There we go. Physics, surface tension working for us. Put that back. Switch hands. Get my clay. Stick it into the clay. Get a plug in there. Good enough. I'm going to take it and place it ever so carefully. Into my centrifuge. And it's probably hard to tell, you can't see it, but what I did is I put one on one side, one on the other side. It has to be balanced, because when this thing gets going, it's going to spin like the wheel of a race car going 200 miles an hour, and it can be kind of scary. So we want to get it balanced so it stays smooth and it doesn't wobble and come alive and fall off the table and scare everyone to death. So it has to be balanced. So I'm doing that carefully, and then I'm going to put this on. This is steel cover. It's got a knob, and I'm screwing it on there. And I want to get it so it's snug. These things are designed to tighten as it turns, not come loose. So you don't want to get it so tight that we have to call an auto mechanic to get it open at the end of the lab. You just want it snug. So now I got the steel lid in place. I'm going to put the plastic lid in place as well. Then I'm going to fire up my centrifuge. It's set like this. You might think you would choose blood for this experiment. No, too easy. That's too easy. No, what we have is set it for this, MHCT. That stands for microhematocrit. That's what we're doing. It's got the special locking button down here so that it shows that you have to be careful here because it spins so bloody fast. Once that's all set up, I just press the start button and it spins at like 1,000,000 miles an hour for 3 minutes. And it takes like another 3 minutes for it to slow down and stop before we can get a result. So I'll just fire that up so you can see what it sounds like. Okay, 60 miles an hour, 100 miles an hour. 150 miles an hour, I'm guessing. Geez, Captain, we're approaching warp 9. Okay. Now, sorry, I turned the dial the wrong way because I was looking the wrong way. I'm used to looking from the front. So I'm going to let it spin down a little bit so you can actually hear me talk instead of this thing going a million miles an hour. Okay, ultimately the end result is it's going to come out looking something like this. Looks similar to when I first put it in, but the whole idea is it spins in centrifuges and it separates the plasma from the red blood cells. So if I lay it down like this, it'll probably be more clear and evident to you. And I'm putting it right on this white piece of paper right next to a millimeter ruler. The idea being we have to measure, okay? Or for French, mesure. So I've lined up the bottom of the red blood cell column with the 0. And of course we use the metric side to be scientifical, not the inches and fractions of an inch. All right? Up here, we're looking for where the red tops out. That's the top of our plasma column. From here, it looks like it is about 6.5 centimeters, or 65 millimeters. And then I'm looking for that place where we see a transition, which, here we go. Let me get this thing again. Yeah, I'm Rocket Man. Where we see a transition between the darkness, which is the packed red blood cells, and the light part, which is the plasma. We want to find that spot there and get a measurement. Okay, so eyeball, rough numbers, I'm seeing about 30 millimeters for the height of the packed red blood cell column. And my total was about 64, 65. So it's easy math for packed cell volume. You take 30 millimeters, divide it by the total, 65 millimeters, do a little bit of math, and that's just a little bit below 50%. I would guesstimate right around 40%, which is a good hematocrit. That's a good number for a healthy sheep who's not quite dead yet. But that's how you do the test. Not too difficult. Okay, stay tuned for the next experiment, the final one, where we check for hemoglobin itself instead of for red blood cells.